Welcome to a new test and teardown video. This time it's a Keithley 2000 multimeter. This one is a really nice one. A 6.5 digit multimeter, so oh yeah, this is definitely something. I think this is about 2007. From the serial label on the back, but we're gonna try and figure that out when we open it. It is made of this type of plastic that turns yellow. Not that it matters anything about how it works or anything like that, but it's just funny. Different types of plastic reacts to UV light, sunlight, and just age. You can see here the bottom side didn't get so much light compared to the front and the top. And this type of sticker here is using another type of plastic, which is coated with something so it's UV resistant. I found one on eBay for about $400, so I think that's quite fair price for a really nice 6.5 digit multimeter. This model is of course obsolete, and today the direct replacement is a DMM 6500. That one is of course a super sexy all touch multimeter. Also it's 6.5 digits, and it is about $1,670, and I think that's a little bit pricey, but it's still fair if you compare it to all the other instruments in this 6.5 digit range of instruments. I like this front and rear switch. All the instruments got this today, so that is a very normal feature. Everything here is nice touch and all that. The display is 12 digit VFD, English flag type of display, so you can display all letters and numbers and all that kind of stuff. On the rear we see of course the rear remote input, options slot, trigger, serial port, and of course the IEEE port. It's very lightweight. The only thing that I found a little bit weird, that's this handle, the way that you pull and all that kind of stuff. It's a little bit, I don't know if I want to say weird, but it's just a little bit different compared to what I'm used to. Do this and do that sticky handle. We got some kind of weird things going on, so if nothing is connected and I go into DC voltage, we have all range, and if you see here, it just counts and counts and counts like that. So what the heck is going on? And it continues until it overflows. So that is a little bit weird. I got a cable here that is shorted in the other end, and if I plug this in, of course it goes to 0. I find it a little bit weird that it just continues to go up like that if it's open, like you see this. So I think this is a leakage, or it's an open resistor somehow. This can't be right. I mean, is it really supposed to do this? We got filters so we can change. So this is 10 readings, average. How do you enter? Type moving average. Okay, cool. So now we got 10 digits. But I've also got rate, medium. I can change the rate to slow. But is that going to change that it just counts and counts? I don't know. As you see here, It just goes on and on and on, and it changes through the ranges, and it just goes on and on. Really weird. Fast, medium. Well, I will go and play a little bit and see if it's at least accurate. So this is open. Let's try and give it about 1.6 volts. So all that is more or less fine. So we are still in the first 15 minutes of power up, and I'm still playing a little bit about DC voltage. So if we see here, it says 59750, and it's going a little bit down probably. And let's look what we got here, 59747. So I think it is quite all right so far. But I think I'm gonna leave it an hour, and then we're gonna do a little compare again. Now I've been running for 3 hours, I think, and it's night and spooky. I changed the voltage a little bit. It is of course a little bit unfair. We are running at 2 volts almost in the 10 volt range, because this one runs in 100 millivolt, 1 volt, 10 volt, 100 volt and 1 kilovolt ranges. So that's just how it goes, right? So if you have close to 2 volt, yeah, you need to be in the 10 volt range, and that is why you have 5 digit after the dot. I am using the slowest possible mode and the highest filter to give a most stable reading as possible. Just while we are at it, why not try all the different meters that I'm using more or less every day here. So the Keithley say 99726 right now, so that is 726 we see on the Keithley. I keep looking at that if it's still the same. So this is where we are. Yes, and this one is quite close to that one. So I still got certificates and everything on that one. So this should be my most accurate unit. At least this is what I call my reference. I trust this one the most because it's brand new and still got valid calibration. Of course you can't count a lot on this. It's plus minus a few millivolts, as you can see here. And that is also within its specification. Remember earlier in this video I complained about the voltage was rising and rising, and I did some experiments in the first 3 ranges of the DC voltage input, and voltage just goes up and up and up and up. And that is because the first 3 ranges of this meter is automatic 10 giga input, and the last 2 voltage ranges, the 100 volt and the 1 kilovolt ranges, they are 10 mega ohms. And just to show you how this looks like on another meter where you can change this or enable and disable the input. So here is 10 mega ohm, but if you go to 10 giga ohm, voltage will just rise and rise and rise until it just flips over all the different ranges. So that is a normal thing, really. Let's look a little bit on the fantastic things inside this really nice Keithley unit. I removed the shield, so we have this shield plate mounted right here. You can see the screw for it here, and that is because this entire area here is the AC input, and this is the RMS to DC converter chip. It's always the same they're using. And look at that, because of input impedance and leakage, creepage, all that kind of stuff. They milled some holes here to fix that real nice and good. The cathode resistors for all the different voltage dividers, they are really nicely made here. Look at that. 4 layers glued together and whatnot. Oh, this is a little bit of a special one, I guess. Yeah, we got the mains transformer all the way up here. This is the display, right? So it's all the way up in the front. That is a little bit untraditional layout for a multimeter. But if you think a little bit about it, it's easier to have the PCB all the way up the back and then have all the connectors going out the back like this. A little bit easier, isn't it? So of course it can be like that. The only thing that is then challenging, that's the mains input wires. They now go all the way. We have a long stick from the front panel on off, and that goes to the mains input and voltage selector. It's quite funny they have this long stick. It's a mechanical challenge to make it like that, and you can even see how much it bends when I push it. And that's because it's not straight, because it's going about here and then go this way to push the switch. I mean, really? And then all those long wires back to the transformer, and then again long wires, AC wires from the transformer going to those 2 connectors just near the AC input. And that is why you need the shielding. That's a little bit double trouble. Of course, we got all the different rectifiers. We got all the analog stuff and all the software department. This one is of course full of software. It's microcontroller doing a lot of cool things. So this is an MC306 running at 14 megahertz. It's a 16-bit microcontroller, so software for it is located in those 2 windowless one-time programmables. It's just a plastic-cased EEPROM, and we got 2 SRAMs, so 8-bit and 8-bit. That makes 16-bit. And here's of course the National Instruments IEEE, a fully programmable IEEE interface. For that one, we also got another little power supply here. Great. The interface from all the hardware, the electronics, software stuff here, right, is going via optocouplers to the digital, to the analog measurement system. That is, of course, to isolate everything. And even see, there's a complete isolation barrier all the way around with a long distance, so there's nothing that is cross-talking. And where it's getting close, they milled a hole so that leakage or any kind of AC here is not going into the tracks here. That one is the voltage reference. If you look at that chip here, it's from Linear Technology, called SL40057 and then IC527. This is a rebranded or renumbered LM399 voltage reference. It is an oven compensated voltage reference, ultra accurate and super nice and good. This one is 0.5 ppm, and if you look at this outer plastic, it's a little bit, you see, it's a little bit loose. So the outer plastic here isolates the little tiny chip there's in here with 4 pins. So there's a heater, temperature sensor, a temperature regulator. Everything is connected to the 2 pins for the heater, and the other 2 pins is a voltage reference and all that, the parts needed to make the voltage reference as good as possible, and that's the other 2 pins. And that means you have your voltage reference extremely accurate. Yes, those LM399s, that's 0.5 ppms. So that is of course needed if you want 6.5 digit readout to the specifications of this unit. And when you come to 80 conversions, it's a little bit tricky what they've done in this unit. They're using a CPLD here, and the CPLD is also the digital interface to the optocouplers, and it is also a dual slope counter for the 80 converter. And that is of course because you want to count very, very fast to get a very high resolution. And inside a CPLD, you can make counters and gates and flip-flops and all that stuff completely synchronous. And that means it takes exactly the same number of clock cycles to reach exactly that time, because there will be unlinearity if you would have built the counters by using a stack of discrete components. So it's very, very critical to make that counter correctly in a dual slope. And here's of course the clock for the dual slope. It's a little bit funny that this one is not an oven clock, because clock for the is also affecting your results. So that's a little bit funny. I've been looking around on the different part numbers here. 98. So I think this unit is manufactured in 98. We see the PCB here is designed in 94. Oh yeah, they're using Teflon cables. That is good. And this is the very, very good, super quality shadow switch for the front and rear input switch. All that is real nice. Oh, I found another funny detail here, by the way. Look at that cable here. So here's a normal standard ribbon cable. It goes into this press-on connector. They cost close to nothing. And of course the PCB part also cost almost nothing, right? Then you have a cable desoldered, tinned, and put into a PCB and hand soldered like that. There's no way you can have a machine do this. So all this rework and handling and doing all this kind of thing manually down here, instead of having those two parts here as well. I mean, you are not saving money here, that's for sure. That is a little bit funny. So this is of course the slide in for the option modules, so you can scan stuff and use it for all sorts of automatic test setups. But wow, is it nicely built, I must say. I kind of like it. Yeah, that's the current sense resistor, and that one will of course run a little bit warm when you are measuring high currents. And see, they try to isolate. See, there's a hole. Oops, I can't see anything here. See, there's a hole here, and that is because they don't want this heat to affect the crystal. That means the time as well. But those crystals here, they can be made so that temperature is not affecting the result that much. But still, it's a little bit funny. This is not an oven, or it's not put somewhere like here, or far away from everything. These two and all this could have been inside a little isolated foam cabinet. Oh yeah, look at that. They're using very expensive, high precision parts, and you see them all over the place. So it really matters, and those are also the good expensive parts. I kind of like it, so full of high performance parts. I'm now in the 100 volt range, and you can see it's nice and stable without anything connected. This is 0.4 millivolt of offset. If we try to short the input, You see? No. Ooh. Yeah, it is some sensitive stuff. So this is in my range here, right? So if I go up to, and then it shows 100 volt, and then see, that is the 10 giga-ohm input range, also in the 10 volt, and then you go to 100 volt, and then it stops doing that. So this is just what you need to be aware of when you're playing with an instrument like this. Also, if you look at the brightness of the different details, you see that medium, this is the rate, this is what's been used most. So it's a dim as everything else, right? So if I click on rate and I go slow, ooh, look how bright that is. That's a little bit funny, isn't it? I kind of like this the slow thing because it's more stable when I want to see the last digit in the experiments I've been playing around with. You can of course also go fast, and then it goes like this, right? But all the specifications needs to be in medium or slow, and it also depends on how many filters. See, I'm going 100 readings of filtering instead of just 10 required. So I get a 10 times as stable readout. Let's look a little bit more on what's going on with the voltage reference. See, it's only 55 on the outside. Oh, we got a little op amp here that's running 70 Celsius. That one down there, wow, crazy. So those LM399s, they got an internal regulated temperature that is 90 Celsius. And then this little shielded isolated case, and it is loose because it really wants to kind of isolate, but it's not super isolated. It's not like a big foam thing, because you want a tiny little bit of heat transport from inside and out, just enough to make the temperature regulation stable. I've been playing quite a lot with these voltage references. Like you can see here, I got some really old LM399s, and I also got the ADR 1399. Yes, and that is almost 3 times as good. In the Keithley 2000 and 2001 and 2010 multimeters, they're using the LM399. As it's only in the Keithley 2002 they're using the more sexy LTZ 1000 reference. Let's turn off the light and show the isolation again. See, here we got those milled lines, we got all the digital stuff, we got all the analog stuff. And if we look a little bit here on the thermal, you can see that the isolation barrier between the digital and analog truly works. They really got everything in here is a little bit warmer, and everything over here is a little bit colder. It's also a little bit interesting to see CPU is not warm, any of the digital parts not warm. Oops, only here. Line drivers for IEEE, those are warm and correctly placed, far away from everything. So it's all come down to good thermal design. Got of course the power supply regulators here running at 70 Celsius. And they are, as you can see, without any heat sinks, and very close to capacitors. So that's probably not the smartest move. You could click on one of these, a little click on, and just this tiny little heatsink here will lower, see? Of course it's not the same watts or anything like that, but it will definitely have a huge effect on those parts, and also how well it couples to the capacitors. You don't want Your capacitor's being warmed up. Oh, what is that? Oh yeah, another little IC down there, running quite warm. That is probably doing some interface with that one. Okay.